So last time we considered trying to find the average rate of change for a particular function, um, f of x equals 3.2x squared. And what we wanted to do is we wanted to find the instantaneous rate of change. That was our goal. We wanted to find the instantaneous rate of change. And the problem that we ran into is that if I try to find the instantaneous rate of change over an interval that has zero length, we end up dividing by zero. And that, of course, is problematic if we try to do it directly. So if we try to do it directly, we kind of get this 0 over 0. But what we noticed is that we don't actually need to find the instantaneous rate or at a particular point by using the average rate of change formula. Instead, what we can do is we can actually kind of consider a trend. We can consider small intervals around 3, and we can see, well, what is the trend of those values? What do those values seem to be approaching? And if we consider for values that are less than 3, so this is kind of from the left-hand side of a number line, because remember, when you're dealing with problems like this, you're dealing with a number line, and if 3 is here and I'm dealing with 2.9, that's to the left of that. Whereas if I deal with something like 3.1, I'm dealing from the right. So even though things are lined up vertically, it's important to consider that the stuff in red is the left-hand stuff, and the stuff in blue is the right-hand stuff. And the key is that when you consider these trends, what you'll notice is that they tend towards this value 19.2. And it turns out that if we look at a trend, so we're trying to find the instantaneous rate of change, and we're using a trend, we actually can extract that it should be 19.2. So the question that I want to ask today is, well, what does this actually mean? How can we formalize this? So the general idea here is that of a limit. Okay, so the idea of basically, and I'm not going to be mathematically precise here, but the idea is that we're finding the value of a function through trends Well, that is basically going to be the idea of what's known as a limit. Now, again, when you find what's called a limit, you're not actually finding a value of a function, but it's going to capture the same essence. If, for example, we were to consider f of x, which is equal to sine x over x, so we're going to kind of deal with a completely different problem. It has nothing to do with finding an instantaneous rate of change, but we're going to still have this issue of directly evaluating, and I say that because you can't, it's still going to be undefined, but trying to evaluate this function at 0. Because if I try to do this at 0, and again, we're considering everything to be in terms of radians here. Well, what is the sine of 0? Well, the sine of 0 is, of course, 0, so that's going to be 0 over 0. It's kind of the same problem. This is actually undefined, okay? But, can we maybe see what happens if we look at a trend? Here we actually see the graph of sine of x over x. As you can see, I've graphed it right here. And if we're looking to see what happens at x equals 0, we'll notice that, well, it looks like it should be 1, right? And actually, it's going to be undefined at that point, even though you can't see it. But there's actually a little bit of a hole there. But if you look at all the values around it, it really looks like it should be 1. And we can actually also verify this algebraically as well. Again, it appears as though f of 0 f of x being sine of x over x should be equal to 1. But as we saw, if we plug in 0 directly, it's undefined. But what if we consider a trend? That is to say, what if we consider what happens if we, instead of looking at what happens exactly at 0, what if we consider what this function is doing around x equals 0? So this is what happens when we actually try to evaluate this function. Again, I'm suppressing the work, but you can check that f of negative 1, for example, is going to be the sine of negative 1 over negative 1, and that's going to be 0.841. And that's what I did for all 8 of these values. And let's see what happens. Again, if I look at, again, everything from the left. So remember, everything over here in red is on the left-hand side of 0. Okay, so that's everything over here, starting at negative 0.1. So again, this is the x-axis. We're suppressing the y-axis here. But you'll notice that there's this tendency of these values to get closer and closer to 1. So it looks as though, like, hey, if I were to follow this pattern, I was going to actually plug in 0. This should be 1. Now, again, 0 is going to be undefined, but it looks as though it should be 1. And same thing when we consider what's happening on the right-hand side. Actually, you end up getting the same values because it turns out that sine of x over x is an even function. But notice it's the same trend. This at 0 here, it looks like it should be 1. It's not. Again, it's undefined. But how do we formalize this process that, hey, this value should be 1? I mean, basically you have, I guess I'll maybe draw a little bit of an axis here. This is 1 here. There's a hole there. But everything over here seems to point towards that it's going to be 1 if you look at all the values around it. And same with everything here as well. So the question becomes, well, how do we indicate this? How do we formalize this idea? And this was exactly the same idea that we dealt with when we dealt with average rate of change. Okay, we basically had this notion that we had a point where we couldn't find the value of the function directly by plugging values in, but if we looked at the trend, we saw that it was equal to 1. So, or whatever the value is in that particular case. So this is what is known as a limit. So what we will say in a problem like this is that we're going to say that the limit as x approaches 0, sine x over x, or sometimes it's the limit of sine x over x as x approaches 0 is equal to 1. Okay? Again, f of 0 itself is undefined. But this is basically how we can notate this idea. So let's provide a general definition now. So again, keep in mind that this is what I would call an informal definition. Later we'll see that we'll have to consider this in a more formal and more mathematical, precise way. But the idea is that if f of x is defined around an x value c, but the key is, but not necessarily at c. Then what we're going to say is that the limit of f of x, so this is any general function now, as x approaches c is equal to L, okay? If as x gets closer and closer to c, f of x gets closer and closer to L. And again, there is a little bit of imprecision in this idea because, again, what do we mean by closer and closer? I mean, in the above example, it seemed like it was pretty clearly, we chose values that were, 0.01. That was pretty close to 0, and this got pretty close to 1. But, this is a relative term, and oftentimes in math, we want more absolute and more rigorous definitions. But I think it's important to look at this more informally at first rather than to overburden you with a formalization. Until maybe perhaps a later time here. And then f of x will get closer and closer to L. Now, when we talk about limits, we talk about both like the existence of a limit and this equality. And this is more of a technical terminology. But basically, if this process happens, okay, we're going to actually say that the limit exists. So the idea is if this happens, and again, I'm being imprecise, we say that the limit of f of x as x approaches c exists. And then also we're going to say and is equal to L. And a lot of math text will kind of make a distinguishment because again, what does this equality actually mean? It's not like a normal equality that you would see in like a normal equation because there's kind of this closer and closer stuff. So we'll talk about limits existing and then we'll talk about them being equal as well. So that is basically kind of our intro into limits. And as we go forward, we're going to see how we can make things more precise, how we can maybe use more algebraic techniques to find limits rather than kind of making tables and kind of doing guessing games like we did here, which can be annoying and tedious at times. And we'll look at all the different ways that we can kind of apply limits, including its rigorous definition. And then we'll also see how it applies back to that average rate of change problem. And that will really lead us into differential calculus. So that's it for today. And I'll see you next time. And take care, guys.